Hey guys, welcome. This is 4.1, max and minimum values. So today's lesson is all about looking for maximums and minimums, or what is also called local extrema, right? So the first two pages are just definition on what maximums and minimums are, local maxes, local minimums, absolute maximums, absolute minimums. So a local maximum occurs if our graph goes from rising to falling. If our graph rises and then falls, then a local high point is created, which is called a local maximum. And this happens on some open interval, AB. So your graph must rise and then fall, and that creates a local maximum, which means the opposite could be said for a local minimum. You have a local minimum if your graph falls and then rises. A local minimum will occur right there in the middle. So your graph must fall and then rise in order to create a local minimum on some interval AB. Okay. All right. Value f of c is called a local extremum if it is either a local max or a local minimum. A point on a graph where a local extremum occurs is also called a turning point, and it's meant to be called a turning point because it's where the graph changes direction. So if I just drew a little sketch down here, let's say here's my graph, and there we go, we have something like that. Well, this would be a local maximum and also considered a turning point because the graph changes direction, because the graph goes from increase to decrease, so it changes direction. Same thing here, that would be a local minimum because we are still decreasing and then we increase. And then another local max, increase, decrease, local min, decrease, increase. So maximum and minimums can also be considered turning points. Okay, there you go. So that's local maximums and local minimums. The next page is about absolute maximums and absolute minimums. And to be an absolute max, you have to be the highest point, the only high point on the graph. So if you look at the graphs below, the second graph here represents an absolute maximum. This point is the absolute highest point of the graph. This is why it's considered an absolute maximum. And then to be an absolute minimum, you have to be the absolute lowest point on the graph, which is represented by the third graph. This point here, 0, 0, is the absolute lowest point of the graph. Okay, and then picture 1 has a local max and a local minimum, but it does not have an absolute max or minimum because this tail is headed towards infinity and that tail is headed towards negative infinity. This means there is no absolute high point and no absolute low point. Okay, so there's your difference. And yes, you can have multiple local maxes, local minimums, and you can even have multiple absolute maximums and absolute minimums. It just depends on the interval that you're on. Okay. Next is extreme value theorem. All this theorem says is that if you have a closed interval AB, then the function that's graphed on this closed interval will have an absolute maximum and it will have an absolute minimum. That's all this theorem says, but it has to be on a closed interval. Okay, so if you look at the graphs below, the interval is closed. So for the first graph, the interval is closed from 2 to 12, and this means that it has an absolute max at 154 and an absolute minimum at 24. Because since the graph is closed off, this is where the graph stops. So you'll have an absolute max and an absolute minimum. Change the interval up to 4 to 10. Absolute maximum changes to 105. Absolute minimum changes to 73. Change the interval again, 4 to 8. Absolute max, 105. Absolute minimum, 78. Change it one more time from 3 to 11. You now have 2 absolute maximums at 105 and 2 absolute minimums at 73. So with that being said, we now want to know how to find these maximums and minimums, which brings us to the next theorems and definitions. So Fermat's theorem says, if f has a local max or minimum at some value of c, and if the derivative exists at c, then the derivative must be equal to 0. So what this theorem means is that in order to find maximums or minimums, we are going to take the derivative, the first derivative, set it equal to 0, and solve for x. That's all we're going to do. And the reason we do that is, well, the next definition. We get into critical numbers. A critical number of a function f is a number c in the domain of f such that either the derivative at this critical number is 0 or the derivative at this critical number does not exist. If f has a local maximum or minimum at c, then c is a critical number of f. So what we do with all this information, just to make it simple, make all of this really simple. To find critical numbers, we take the first derivative, we set it equal to 0, and we solve for x. That's it, okay? That's all we're gonna do. When we get to the closed interval method, just one thing's gonna change. What is it? Sorry, it's Sunday. So only one addition will come when we use extreme value theorem. So local absolute maximums and minimums on a closed interval will happen at critical numbers and or will happen at endpoints, but when we get there. So for now, all we want to do is practice finding critical numbers. And to find critical numbers, you take the first derivative, you set it equal to 0, and you solve for x. And if we are given a rational function, which this problem will become, you want to get critical numbers from the numerator, and you want to get critical numbers from the denominator. So that's what we're going to do. Okay. So number 1, find the critical numbers. So the first thing we're going to do is take the derivative. But before I take the derivative, I'm going to distribute this x to the 3/5. It's going to make our work easier, unless you really, really want to use the product rule. Your call. I'm going to distribute it. So if I distribute this, I get f of x equals 4x to the 3/5 minus x to the 8/5. X to the 8/5. That's because when you do this x and that x multiplied together, that's x to the 3/5 times x to the 1st. Make that into 1 over 1. Multiply it by 5/5. And you get x to the 3/5 plus 5/5, which gives you x to the 8/5. That's where that comes from. Okay. Perfect. So I distribute it, and now I'm going to take the derivative. Let me take the derivative now. So f prime of x is equal to, that's going to be 12/5 x to the negative. If I take 1 away, that's 2/5. X to the negative 2/5. Minus 8/5 x, take 1 away, that should be to the 3/5. Okay, so there's the derivative. So maybe we should make it look pretty before we set it equal to 0. So that's what we're going to do. Let's make this look pretty. And when I say that, well, I can factor out a 4/5. So I'm going to take out a 4/5. And at the same time, I'm going to take out the smallest x power, and the smallest x power is x to the negative 2/5. So that's what I'm going to factor out. I'm going to take out a 4/5 x to the negative 2/5. And if I factor that out, 4/5 from 12/5 should just be 3. And I should just get 3 here, minus 4/5 from 8/5. That should give me 2. And then x to the negative 2/5 from x to the 3/5. That's just going to leave me with x. Okay. Oops. Don't erase, just get rid of that. Oh well. There you go. There you go. Okay, so if you're trying to see what that x to the negative 2/5 from 3/5 means, remember that factoring is essentially dividing it from each term. So when I do x to 3/5 and you take out an x to the negative 2/5, well, this negative exponent means it's going to flip to the top, which gives me x to the 3/5 times x to the 2/5, and then you add your exponents, giving me x to the 5/5, which is just x to the first, or x. That's all that's going on. Okay. Simple, right? Okay, still moving. It's almost pretty. Now, what I want to do is take that x to the negative 2/5 and flip it to the denominator. So that means we get f prime of x equal to 4 times 3 minus 2x over 5x to the 2/5. There's the first derivative. Now, let's set it equal to 0. So let's do that. What room am I working with? Oh, I got a lot of room. Okay. So now we're going to say f prime of x equal to 0. This means we take this whole derivative, 4 times 3 minus 2x over 5x to the 2/5, and set it equal to 0. Okay, since this is a rational equation, we want to get critical numbers from the numerator, and we want to get critical numbers from the denominator. So that's what we'll start with. I'm going to say numerator. And I take 4 times 3 minus 2x, set it equal to 0. I don't need that 4. I divide it off. I get 3 minus 2x equal to 0, which gives me 3 equal to 2x. And this means that x is equal to 3/2. This is my first critical number. Okay, and then I want critical numbers from the denominator. So I'll go there next. Denominator. Hopefully that's about right. And I take the denominator, 5x to the 2/5, and I set it equal to 0. I divide by 5, and I'm left with x to the 2/5 equal to 0. Okay. So yes, we know our answer is going to be 0, but how do we get there? And the way you get there is, well, you can raise both sides by the reciprocal power. That's the fastest way out of this. I can say all of this raised to the 5/2, and this raised to the 5/2. Because power to a power is multiplication, which gives me 10 over 10, or just 1. So this just becomes x, and 0 raised to the 5/2 is still 0. Okay, and here's our second critical number. There is one thing to notice though. Yes, we're just solving for critical numbers. So 0 and 3/2 are my critical numbers. At these numbers is where maximum and minimums could exist. But we also have to note that for this derivative, can x actually be equal to 0? And that answer is no, because it makes the denominator 0. So just something to think about. But this goes along with the definition on the second page. So the derivative exists at the critical number of 3/2, but the derivative cannot exist at the critical number of 0. Now, if I scroll up and explain what I'm talking about, look at the definition under Fermat's theorem. A critical number of a function f is a number c in the domain of f such that the derivative at this critical number equals 0. That's 3/2. If I plug 3/2 into the derivative will become 0. So we check out there. But then, or the derivative does not exist at that critical number. Can the derivative exist at 0? And that answer is no, because the denominator becomes 0. So just check your domain. That's why on a rational equation, we set the numerator and denominator equal to 0. So just look out for that. That's coming later. Okay, perfect. All right, so that's finding critical numbers. Simple. Take the derivative, set it equal to 0, solve for x. Next is the closed interval method. So now we're going to be given a closed interval. We're going to find critical numbers, as we did on the last example. And then all we have to do to find an absolute max or minimum is test the critical numbers in the given interval and only test the endpoints in the interval. That's it. We don't need any other numbers. That's what this says right here. Find the values of f using the critical numbers and the endpoints of the interval. And whatever the largest y value is, will be your absolute max. And whatever the smallest y value is, it'll be your absolute minimum. That's it. And if our critical numbers happen to not fit in the closed interval, well, we just ignore them because we don't need them. That's it. Okay. So 2, find the absolute max and minimum values of the function. f of x equals x cubed minus 3x squared plus 1. And we're given the closed interval of -1/2 to 4. So that's the interval we want to work on. Okay, so just like the other ones, we want to find critical numbers first. So we're going to take the first derivative. So we can say A. Find critical numbers. And that means we take the derivative and we get 3x squared minus 6x. All right? Yes. Then that's nice already. We take the derivative and we set it equal to 0. 3x squared minus 6x equal to 0. Factor out of 3x, that leaves me with x minus 2 equal to 0. Then set both of these equal to 0, and I'll get x equals 0 and x equals 2. These are my critical numbers. Okay, excellent. So that one was really nice, right? So all we have to do now is test the endpoints with the critical numbers. Okay, so B, test endpoints and critical numbers. And all I'm going to do here is make an XY chart. Here's X, here's Y. I'm first going to put in my endpoints, which were -1/2 and 4. -1/2 and 4. And then I'm going to take a peek at our critical numbers. On the interval -1/2 to 4, do my critical numbers of 0 and 2 fit in that interval? And the answer is yes. 0 and 2 fit in the interval -1/2 to 4. So I will put my critical numbers on this list as well. 0, 2. Okay, so we're looking for an absolute maximum and minimum of the original function. So you are going to take these points. You're going to take all these values and you are going to plug into f of x, because we're looking for max and minimums on the original function, not on the derivative. So plug these into the original function. And my original function's up there. Let me see. I have x cubed minus 3x squared plus 1. Enter, enter, enter. And now come down and I'll type these values in. -1/2, I get 1/8. 4, I get 17. 0, I get 1. And 2, I get -3. So now, all we have to do is look for the largest y value and the smallest y value, label them my absolute maximum and minimums, and we're done. That's it. So my largest y value looks to be 17. So the point 417 is my absolute max. And then -3 is my smallest y value. So this becomes my absolute minimum. That's it. We're done. Nothing more to it. Of course, that was an easy one, huh? Okay, perfect. Okay, but that's it. That's how you find critical numbers, and that's how you test them on the closed interval method. All you need are the endpoints of the interval and the critical numbers. Make sure your critical numbers fit in the interval. If the critical numbers do not fit, we do not use them. Simple as that. That's all. Okay. All right. Practice. So basically the notes are over. So now this is just fun. So now you just get to watch me work. Find the critical numbers of the functions. So we're given, did I get a whole page for that one? Yep. Okay. So this one, we're just looking for critical numbers of the functions. So this is going to be quotient rule. So numerator's f, denominator's g. F is x minus 1. G is x squared minus x plus 1. F prime is 1. G prime is 2x minus 1. Follow your quotient rule. And I start off with g prime of x, and you get f prime g. So x squared minus x plus 1 minus g prime f, 2x minus 1 times x minus 1 all over x squared minus x plus 1 squared. Okay, clean up, maybe make this faster. This becomes what? 2x squared minus 2x minus x plus 1, which becomes 2x squared minus 3x plus 1. Okay, all right, 2x squared, negative 2x, negative x plus 1. Okay, so which means I move to my next step. G prime of x is x squared minus x plus 1 minus 2x squared plus 3x minus 1, still over this denominator squared. Last cleanup, g prime of x is equal to negative x squared plus 2x. That's it. Negative x squared plus 2x, your ones cancel, over x squared minus x plus 1 squared. Okay, now we're just looking for critical numbers. So let's set g prime of x equal to 0. And that's negative x squared plus 2x over x squared minus x plus 1 squared equal to 0. And just like the very first example, we'll start with the numerator, which gives me negative x squared plus 2x equal to 0. Take out a negative x, I get x minus 2 equal to 0. This means x equals 0 and x equals 2. These are my first set of critical numbers. Let's get critical, critical. Let's get critical, critical. Sorry, it's Sunday. And we'll start with the denominator, denom. And we get x squared minus x plus 1 equal to 0. And what we notice is that, hey, there are no factors of 1 that make -1. So the only other way we know how to factor is by completing the square. Don't be such a square, okay? All right, which means move that 1 over to the right. X squared minus x equals -1. Complete the square, CTS. Take half of the middle term's coefficient, which is -1, -1/2. Square it, you get 1/4. Add that to both sides. X squared minus x plus 1/4 equal to -1 plus 1/4. And then factor the left side. Remember, after you complete the square, the whole left side becomes factorable, okay? So this becomes x minus 1/2 squared equal to -3/4. And then square root both sides. And what do you see that happens here? You get x minus 1/2 equal to plus or minus. And can you take the square root of a negative number? The answer is no, because it gives you imaginary numbers. So you would end up with I square root 3/2. And we stop there because this means that my imaginary numbers, or my critical numbers, are imaginary. So we don't go any further. Ugh, there we go. Yay, there we go. All right, so we don't use those. No need. All right, so the only critical numbers were 0 and 2 from the numerator. All right, beautiful. Look how gorgeous that looks. All right, let's keep going. Like I said, I'm here for your entertainment. Mushroom bed, or with lots of it. Okay, same thing. We're finding critical numbers. Let's do it. Let me rewrite this first as f of theta equals 2 cosine theta plus sine theta squared. So sine squared theta, I'm rewriting as sine theta squared for derivative chain rule purposes to make it look nice and neat. Okay, now we're ready for the derivative. F prime of theta gives me -2 sine theta plus 2 sine theta times the derivative of the inside, cosine theta. Okay, let's pretty this up a bit. F prime theta, I can take out a -2 sine theta. I take out a -2 sine theta. This leaves me with 1 minus cosine theta. 1 minus cosine theta. Okay, perfect. We're ready to go. We take the derivative and set it equal to 0. negative 2 sine theta times 1 minus cosine theta equal to not that, 0. Okay, and set both of those equal to 0. So negative 2 sine theta equal to 0. 1 minus cosine theta equal to 0. And then divide by negative 2, you get sine theta equal to 0. So now, here's where you remember your unit circle, right? Where, and lucky, but before I even start, we only want values on the unit circle. These restrictions are here, and we only want values that are on the unit circle, okay? That's it. So now we come down, and we say, what values of theta on the unit circle make the sine function equal 0? And those radian values happen to be 0 radians, pi radians, and 2 pi radians. These are the first set of critical numbers. Okay. And then here, move cosine over, or whichever, doesn't matter. I say 1 equals cosine theta. And now, we think to ourselves, where on the unit circle between 0 and 2 pi is cosine equal to 1? And you guessed it, that's at 0 radians and not pi, because pi makes cosine negative, so back at 2 pi. There you go. Okay, there you go. There's the second set of critical numbers. There you go. Okay, let's say that these restrictions weren't given. Let's say 0 to 2 pi was not given. Let's say that you needed a solution to represent infinitely many solutions. Well, for sine, for it to be 0 all the time, theta, right? Theta would have to be what is happening at every pi, right? It's happening at every pi. So I would make theta equals pi k, where what? Where k is any integer. 0, pi, yeah, pi k. I think that's it. Pi k. Okay. And the same for cosine. It would be, happens every 0 and 2 pi. So for cosine, it would have to be 2 pi k, where k is only even integers. So here, k has to be even. Here, k is any number, just in case you don't have restrictions. These can represent the solution of 0 infinitely many times. 1 pi, 2 pi, 3 pi, 4 pi, no matter what, sine would be 0, and then 2 pi k, yep, that'd have to be even. Okay. Just helping you out there. Okay, perfect. All right, still going. This is just critical numbers still. Okay, this one will use product rules. So there's F, there's G. So f is x to the negative 2, g is the natural log of x, f prime is negative 2x to the negative 3, g prime is 1 over x. Okay, follow the product rule. F prime of x, f prime g, negative 2x to the negative 3 natural log x plus g prime f, that's 1 over x times x to the negative 2. Okay, cleanup time. This becomes f prime of x equal to negative 2x to the negative 3 natural log x plus, well, this is also the same as x to the negative 1. So x to the negative 1 times x to the negative 2 is x to the negative 3. Do you see something we can factor out? Of course. F prime of x, I'm just going to take out an x to the negative 3. And that leaves me with negative 2 natural log x plus 1. Okay, and one more rewrite. That x to the negative 3 we can flip to the denominator. So f prime of x equals negative 2 natural log of x plus 1 all over x cubed. Now we can set it equal to 0. Negative 2 natural log x plus 1 over x cubed equal to 0. And now, since it's rational, we'll have something from the numerator, which means we'll have negative 2 natural log x plus 1 equal to 0. Okay. Solve for x. Move that 1 over. Negative 2 natural log x equals negative 1. Divide by negative 2. Natural log x equals 1/2. And now, to get the x out of the natural log, convert from log to exponential. So I can put that little e here if I want, and this becomes e to the 1/2 equal to x. There's our first critical number. Okay, and if you want, type that in your calculator. You should get something like 1.65. Rounded to 2 decimal places. Okay, and then of course we have the denominator. So much room, sorry. Hey, look, and you know that denominator, it's going to be really easy. Denominator, we get x cubed equal to 0, therefore x equals 0. These are my critical numbers. Marvelous. Okay. Now we're back to finding absolute maximums and minimums. So not much changes, same process. All we have to do now is test our endpoints and our critical numbers. So here we go again. So first thing, find critical numbers. So take the derivative, 6x squared minus 6x minus 12. 6x squared minus 6x minus 12. Take your derivative, set it equal to 0. 6x squared minus 6x minus 12 equal to 0. This is an equation, so I can do what I want, which means I'll just divide everything by 6. And I'll get x squared minus x minus 2 equal to 0. Factor that, I get x minus 2x plus 1 equal to 0. X squared, x, negative 2. Good. Set them equal to 0. My critical numbers are 2 and negative 1. Critical numbers. Okay, now we want to test them in the interval above, negative 2, 3. So x, y chart. All right, there's negative 2, there's 3. Do my critical numbers fit in that interval? Do these fit in that interval? 2 fits and negative 1 fits. We're good to go. So I'll put them in. 2, negative 1. And remember, plug these into the original function, right? We take these numbers, and we plug them into f of x. Okay, I'm gonna use my calculator, use the little table trick to make these faster. 2x cubed minus 3x squared minus 12x plus 1. Negative 2. I get negative 3. 3, I get negative 8. 2, I get negative 19. And negative 1, I get 8. Okay. This means that the largest y value is 8. So here's my absolute max. The smallest y value is negative 19. There's my absolute min. Done. Not bad at all. Okay. Oh, again. B. X and the square root of 4 minus x squared. So this is going to be a product rule. So let's make our lives easier here. So I make this behave computer. F of x equals x times 4 minus x squared to the 1/2. Okay. Then product rule. Here's F. I'll change color. Here's F. Here's G. So F is x. G is 4 minus x squared to the 1/2. F prime is 1. G prime is 1/2 times 4 minus x squared to the negative 1/2 times negative 2x. And then G prime gives me negative x times 4 minus x squared to the negative 1/2. Okay, finish up my product rule back here. F prime of x is 4 minus x squared to the 1/2 plus G prime F, that's negative x squared times 4 minus x squared to the negative 1/2. Cleanup time. I am going to factor out 4 minus x squared to the negative 1/2. So that's what I'm taking out. 4 minus x squared to the negative 1/2, bracket for neatness, and 4 minus x squared to the negative 1/2 from 4 minus x squared to the 1/2. Remember on that very first example, the negative would flip up and the exponents would essentially just cancel. So that would leave me with 4 minus x squared minus x squared. Okay. If you don't know what I'm talking about, I'll write that down really fast. So you have 4 minus x squared to the 1/2 over 4 minus x squared to the negative 1/2. That becomes 4 minus x squared to the 1/2 times 4 minus x squared to the 1/2. Same base, add your exponents. 4 minus x squared to the 2 over 2, or just 4 minus x squared to the first. That's it. That's all that happened there. Of course, in less words. Okay, now one more chance to make it pretty. F prime of x equal to, in the numerator, I'm left with 4 minus 2x squared over the denominator of the square root of 4 minus x squared. Now, set it equal to 0. F prime of x equals 0. 4 minus 2x squared over the square root of 4 minus x squared equal to 0. And again, this is rational, so we want something from the numerator. 4 minus 2x squared equal to 0. Move that over. Just move the 4, why not? Looks better that way. Negative 2x squared equals negative 4. Divide by negative 2. X squared equals 2. And then square root. And x equals plus or minus square root 2. There's the first set of criticals. Then we want the denominator. And I only have to set the inside equal to 0. So 4 minus x squared equal to 0. 0. 4 equals x squared. square root, plus or minus 2 equals x. These are my critical numbers, my crits. Okay. Okay, well, now we have to see, do these numbers fit? Do these numbers fit on this interval, right? Do they fit on this interval? And let me make my little XY chart here. X, Y. I'll first plot my endpoints, which were what? Negative 1, 2. Negative 1, 2. Now, does square root of 2 fit in there? Square root of 2 is 1.4. So positive square root of 2 fits, but negative square root of 2 does not. Negative square root of 2 is negative 1.4, which is below negative 1. And then 2 fits, because that's an endpoint, but negative 2 does not fit, therefore we don't worry about it. So we only use these 3 numbers, and I plug them into the function above. X second square root 4 minus x squared. X square root 4 minus x squared. Negative 1, I get negative 1.73. 2, I get 0. Square root of 2, I get 2. Okay, largest number is 2. Here's my absolute max. Smallest number, negative 1.73, absolute min. There it is. Okay, perfect. Hey, look at that, last one. Find the critical numbers of this on those endpoints, 0 to pi over 2. Okay, let's take the derivative. This is going to be a chain rule. So f prime of theta is negative 2 sine theta plus chain rule this, right? Derivative of sine is cosine, so you get cosine 2 theta times the derivative of the inside 2 theta, which is just 2. Okay, so f prime theta is negative 2 sine theta. Oh, where'd it go? Oh, I got rid of the wrong thing. 2 plus 2 cosine 2 theta. Okay, we want to set this equal to 0, but if we set it equal to 0 now, nothing's going to happen because we want this to be in terms of one trig function, if possible. So this means whip out your trig identities, trig formula sheets, and find the identity for cosine 2 theta that could possibly help you. And that identity should be, what is it? 1 minus 2 sine squared theta. That's what that becomes. So f prime theta is equal to negative 2 sine theta plus 2 times 1 minus 2 sine squared theta. Distribute the 2, negative 2 sine theta, plus 2 minus 4 sine squared theta. Yeehaw. All right, fix this up, make it look a little pretty. Rewrite this highest power first. Negative 4 sine squared theta minus 2 sine theta plus 2. And now let's set it equal to 0. F prime theta equal to 0. Negative 4 sine squared theta minus 2 sine theta plus 2 equal to 0. This is an equation. I do what I want. So I'm going to divide everything by negative 2. And I get 2 sine squared theta plus sine theta minus 1 equal to 0. And now, does this factor? And the answer is yes. You get 2 sine theta plus 1, no, minus 1, and then sine theta plus 1 equal to 0. 2 sine squared, 2 sine minus sine gives me sine, and then that give me negative 1. Perfect. Set these equal to 0, and you'll get sine theta equals 1/2, and sine theta equals negative 1. Okay. Look at your unit circles and ask yourself, where on the unit circle is sine equal to 1/2? What radian values give me 1/2? And that answer should be pi over 6 and 5 pi over 6. And then for sine equal to negative 1, look in your unit circle, that happens to be 3 pi over 2. These are my critical numbers. Now, do these critical numbers fit? Do these fit in that interval, 0 to pi over 2? 3 pi over 2 definitely does not. 5 pi over 6 definitely does not. The only thing we know that fits is pi over 6. So let's make that XY chart. And we're using 0. We're using pi over 2. We're using pi over 6. Okay. Plug it into that. Make sure your calculator is in radians. Make sure you're in radians. Okay. Let me make sure mine is. We are. Table feature 2 cosine x plus sine 2x. Enter, enter, enter. Let's go down. And if I type in 0, I get 2. If I type in pi over 2, I get 0. If I type in pi over 6, I get 2. Perfect. This means that I have 2 absolute maximums. And then I have 1 absolute minimum. There we go. Okay. And that's it. That is how you find maximum and minimums and test them on an interval. All right. There you go, guys. Much more to come. Okay. Did my computer freeze? No. Oh, well. It's over, right?